theory is a bonding theory, and it's the most complete bonding theory that people have today. In the other bonding theories, there's often an exception to the rule or a place where it didn't work. This is not the case with the molecular orbital theory. Now, the molecular orbital theory is a very, very complicated. So with that being said, I'm only going to go over the basic ideas and how to read the graphs. And it's because it's not really necessary to know it in so much detail, unless one wants to become a quantum physicist or a quantum chemist. Most of the time what we're going to be doing is just interpreting the information that one of these types of people will give us, and all we really need to know for that is just the basics and the graph, because that's easy to interpret. So what is the molecular orbital theory? Well, it's very similar to the atomic theory. The atomic theory tells me that when I've got an atom, the electrons have specific energy levels, and we found out what those things were. They're 1s, 2s, 2p, 3s, 3p, etc. What happens to these things when there's a bond? Are there still specific energy levels? And the answer is yes. But they're not the 1s, 2s, 3s, 2p, 3p anymore. They change. That's where the molecular orbital theory comes in. It's basically applying those ideas about defined energy levels to a molecule. And the rest of the time, we're just going to be having a look at what those molecular orbitals are. So when a bond takes place, there is an overlap between two orbitals. Here's a 1s orbital, here's a 1s orbital. When they overlap, there is interference. They form a molecular orbital. So when this happens, the old energy levels are gone. They're destroyed. And they form these molecular orbitals. Well, let's have a look at what these molecular orbitals are. First thing there is to know is that there are two types of molecular orbital. There are molecular orbitals where there is constructive interference, and there are molecular orbitals where there is destructive interference. A molecular orbital with constructive interference is called a bonding orbital, and with destructive interference is an anti-bonding orbital. Now I'm going to look at the overlap for the s orbitals. Now, for the s orbitals, and for any other orbital, there will always be bonding and anti-bonding orbitals. For the bonding orbitals, here are the two nuclei. The electron density will be in between the two nuclei. And the atomic orbitals, it was a circle. It's this shape here. Same idea, it forms shells as it goes out. Basically exactly the same as atomic orbitals, but it's shaped differently. And it's a little bit different because we have these anti-bonding orbitals as well. And this is the anti-bonding orbital, it's the same nuclei, but the electron density is around the outside. So this is the area in between this around the outside. So it's easy to see why this is called a bonding orbital and this is an anti-bonding orbital, because the electron density, when it's in between the two nuclei, it helps to form a bond. If the electrons are around the outside, this is a higher energy than it would be if they were in between. So it does not help to bond. That's the s orbitals, and we'll go over one more type of orbital, which is the p orbital. Again, for p orbitals, there are two types of orbitals. There are going to be bonding orbitals and anti-bonding orbitals. But the p orbitals, there's a little bit more to it, because there are three p orbitals. in the atomic orbital theory. So how do these overlap? What I need to do is have a look three-dimensionally what's going on, and it'll be better explained. So p orbitals, the way they are oriented in space is like this. They have one front and back. They have a couple side to side. And then they have lobes that are above and below. So thinking of two p orbitals, how would they overlap with each other? Well, there are two main ways they can overlap. They can overlap front-facing, like this. And that's what this illustration is of. Front-facing overlap. And then the other two types of overlap are equal. They're just side overlaps, and it doesn't matter if it's the side ones or the above and below. It's the same type of overlap, and that is what this overlap is. And again, not only are there two types of overlap, but then there are two other types of bonds, the bonding and anti-bonding. So for the front-facing overlap, there is constructive overlap. This is bonding. And there's destructive overlap. This is anti-bonding. Oh, I forgot to go over this notation. For the s orbitals, this is called a sigma s, and this is for bonding. And for anti-bonding, this is called sigma s star. The star denotes anti-bonding. Back to here. For bonding, front-facing, sigma p for p orbitals. And for anti-bonding, sigma p star. For the side bonds, they can overlap in this manner, above and below, or side to side. And the plus and minus signs, this is not the charge, this is the phase. Like it's like when someone takes a guitar string and plucks it. So this would be positive phase, and this would be minus phase. Just a vibration, not a charge. That's one thing to know. So I did that. Okay. So for side bonds, yeah, I did that as well. Doesn't matter. It would be positive and minus phase sideways or above and below. And for the anti-bonding, this is what this would look like. It's a complete mess. This would be called pi p, and this would be pi p star, anti-bonding. That's the notation. There are d and f orbitals as well, but if one can understand the principles of how this works, when you look at what happens in f and d, then it just makes sense. No point going over it. It's less common. Not that it's less common, but more often than not, we'll be learning organic chemistry after this, and it's less common there for sure. This is how to look at a graph for molecular orbitals. We've got the atomic orbitals on either side of it, and they just fall into the new molecular orbitals that are formed. So this is diatomic hydrogen. This is hydrogen by itself. And they just fall in. And they fill in the new molecular orbitals as I would fill in orbitals in the atomic model, where if there's an empty orbital, whichever one's in the lowest energy, that's where the electrons go. So here's an example of one with more electrons. I'm just going to cross them off as I go in. So I start with one of each, they fall into here, the sigma 2s, then they go into the sigma star, it's an anti-bonding orbital, and then these 2p each go into a pi 2p orbital. If there's an open orbital available, it goes into it, just like when I was filling in the p's going this, and then I started filling them up here. And these, I guess I'll say a couple of things about the charts. These charts will not always, these charts will not always look like this. Often I'll have things of different energy levels. So if I had a fluorine and a hydrogen, this is a 1s, and here it's going to have p orbitals. So the molecular orbitals will be not looking like this, very evenly distributed. And if there's a polyatomic ion, then it gets very, very complicated quickly, especially if there's delocalized electrons. So I guess my point is, it's just really don't focus on what's going on here. Just know the basic principles. They fill in the lowest orbitals, because these orbitals can also change order as well. This is not pi p does not always come before sigma. Did I put s there? Before sigma p. Every single molecule is its own unique system, and as a result, all of the molecular orbitals will be different. Often, for things like diatomic molecules, they'll be close because they're very similar. Or things that are very close to each other, like oxygen and carbon, or oxygen and nitrogen, things that are very nearby each other, then it's not such a big deal. But as soon as I have a significant difference between the energy levels, then all hell breaks loose on these charts. So just that should probably be enough. Also, one more thing to know is when there are single electrons in these what was I saying? Molecular orbitals, it will have magnetic properties. It'll be pulled into a magnet. So that's one piece of information we can know about a molecule from its molecular orbital diagram. Also, what's important to notice, I think I failed to mention this, is that these anti-bonding orbitals, they're a much higher energy level than when they're on their own. So this is conducive to bonding because I've got a 1s energy level, and when they bond, this energy level is lower than the 1s when they were just by themselves, so it's conducive to bonding. But if they are having to go up here, this doesn't help bonding because this is a higher energy level. And it's not to say that anytime electrons go in a higher energy level, there will never be a bond. But it will probably be a weaker bond, or it might not happen at all. In this case, this would be helium, and whenever we find helium in nature, it's always just by itself. Hydrogen, when we find it in nature, is like this. And when I look at why that is likely the case, well, all I need to do is look at the molecular orbital diagram and see that if a bond were to take place, electrons would have to go into the sigma 1s star orbital, and that's higher energy level. Why would it want to do that? It's fine the way it is. That's another main point of these molecular orbital diagrams, is it really helps us have a look at the energy levels, and from those energy levels be able to predict whether a bond will take place or not.